today. So in the lecture about clustering, we talked about one's hard clustering, one soft clustering. For hard clustering, we talked about k-means. For soft clustering, we talked about expectation maximization algorithm. So 2 different things we talk about in this lecture, both quick. K-means is super easy. So k-means is shown in the first picture. So in the first picture, we see that we have data that is actually stemming from different clusters. So I don't know, maybe this is the petal length. Okay, this does not make sense because those are negative values, but fuck it. So let's just imagine this is petal length of flowers and this is color intensity of flowers or something. And then we have actually 4 different flower types. So each flower type is creating its own, unique data points given its own specific mean of the cluster and its own specific covariance matrix for the cluster. In k-means, we fuck the covariance matrix, the cluster-specific covariance matrix, because as you can see, like there are these unique, there's this unique form that is created by the covariance. It's basically saying how much feature 1 is covariant with feature 2, but we just ignore it. The only thing in k-means that we are interested in is actually the centroid, the mean of a cluster. So for instance, we have, this is a random example, we have lilies and tulips and roses and Gänseblümchen, not sure what that is, daisies. And each has their own mean regarding the one feature and their other feature. And in k-means, we get to that mean. In k-means, actually, we say an instance belongs to that cluster whose mean is the closest. So if this point is here, then the closest is this mean here. I mean, it's also kind of close to this mean, but it's closer to this mean. Therefore, it belongs to the cluster roses. Just imagine sometimes in real life there are also a little bit crippled roses. It can also happen that we have a really small petal length and a really small, just a small petal length, normal color intensity, then the data point would be here. If the data point would be here, however, we could not recognize that it actually belongs to this cluster because it's just closer to this cluster centroid. So that is the intuition, that is the idea how we cluster. Now, how do we get to the cluster centroids? We get to them iteratively. In the beginning, we just initialize them randomly. So bing, 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 randomly. We initialize central. So we say we want 4 clusters, or we want 6 clusters, or 2 clusters. This is a hyperparameter we need to choose. So here we said we have 4 clusters, which is cool because we actually also have 4 real clusters in the real world, which we don't know, but luckily it matched. So now we create 4 random centroids. Boom, 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 boom. And then this is the first step. And then the second step is now we check the data points to which cluster does one data point belong. And then we measure the difference between this data point here to this centroid, to this centroid, to this centroid, and to this centroid. And then we assign this little guy here to the cluster that has the closest centroid. So let's say, boom, it's belonging here. It's belonging to this cluster. So we do this for all data points now. So now we have assigned all data points to our clusters that actually have random means. Now, this was the second step. Now we start with the first step again, where we had just random centroids, but now instead of random centroids, we actually recompute the centroids. So we say all of those data points were assigned to the cluster with the centroid here. So now we take the mean value regarding feature 1 and regarding feature 2, all of the mean value of these data points, and then now we get a new value for our centroid, which, boom, is going to be here. So our centroid moves from here to here. So this is then again the first step, and now the second step is again we assign all values to the closest cluster centroid and then decide, and then we do this again. So now we have like a new centroid, so now we have a new assignment. Now again we compute the average, so the average of those values to create to update the centroid again. So bottom line is, first of all, we randomly initialize the centroids, then we assign the data points, then we recompute the centroid, then we reassign the data points, and so on until it converges. And since we randomly initialize the centroids and we do not have a convex learning problem, we can sometimes end up in weird places. So we just repeat this a couple of times, sometimes. And then, on average, we should get like a structure kind of like this. However, the problem is that clusters also have a unique covariance matrix, which is kind of important. So we completely disregarded the fact that they all have their own covariance matrix. And actually, this is especially apparent that it's important when we look at this example here. So here we have actually two clusters, this cluster here and this cluster. So it's kind of like, okay, to be honest, I'm too lazy for an example, but we have two clusters. They have like totally opposite covariance matrices. So for one cluster, the bigger xi, the bigger x2, and the other one has a reverse relationship with x1 and x2. So in k-means, we just measure the centroid and then take what's closest to the centroid. But the problem is that we cannot grasp, we cannot take this covariance information into account. And expectation maximization algorithm accounts for that. So in expectation maximization algorithm, we have two steps. First the expectation step and then the maximization step. And in the expectation step, we take one. So as you remember for k-means, in the beginning we randomly initialized the centroids. Now what we do not only assume the centroid as the important parameter of our distribution, of our cluster, but also the covariance matrix. So now we randomly initialize a centroid, mu, and a covariance matrix. And now we say, basically with the intuition, each data point was drawn from nature, from these distribution parameters. And we have normal distributions for each item. So let's say this is roses and this is lilies, although it doesn't make too much sense, but fuck it, we just do it. So roses are, on average, they have like a petal length of something and a color intensity of something, and they vary. Like the bigger the petals, the more intense the colors would be. Fantasy example. So now the nature draws each instance of roses according to the mean value and also to the covariance matrix, which in this case is the bigger the petal length, the more color intense. And so we randomly give these parameters. So we choose the hyperparameter again. We want two clusters, and then now we initialize two for both clusters random values for mu and for the covariance matrix. And now we have our parameters, and now in the second step, and so this was the very beginning, and now we get to the first step, the expectation step. So we look at one data point and we check how likely has this data point been generated by a distribution with those parameters from cluster 1, and how likely is this data point drawn from the distribution from cluster 2. And then maybe this data point is going to be quite probably drawn from cluster 1, but it's really unprobably drawn from cluster 2. So now we have, for this one, we have a high probability for being drawn from cluster 1 and a low probability of being drawn from cluster 2. Now we normalize this value by taking the probability of this being drawn from cluster 1 divided by the probability of taken from cluster 1 plus probability of coming from cluster 2. And we do the same thing. We normalize the probability of this data point being drawn from cluster 2. So now we will ultimately, we are almost done by the way, so we have a data point, and we have basically at the end we have a probability that it's coming from cluster 1 and from cluster 2, and those values will add up to 1. This is why we did this normalization. Okay, So this was the first step, expectation. So what do we expect to which algorithm does it, to which cluster does it belong to more likely? And it's also soft because we do not assign it fully to one cluster. We just say with a 80% chance it's belonging to this cluster, with a 20% chance to this cluster. And now we get into the second step of the maximization, and then we're almost done. So in the second step, we now update. So in the very beginning, we initialized our distribution parameters mu and covariance matrix. Then we had the expectation where we said, okay, these data points, how we fix the cluster parameters, how likely are my data points coming from one cluster or the other. Now in the second step, we fix the data points, or the data point assignments, the probability assignments, we fix those. And now we adapt our cluster distribution parameters again, mu and covariance. And then after we updated the parameters, we again take each data point and say, now with what probability is this data point drawn from cluster 1? With which probability is it drawn from cluster 2? But now with the updated values. And so we iterate again from expectation to maximization to expectation to maximization until we converge, just like in the k-means. And just as a detail, so this is how we actually update our probability, our cluster parameters. So basically, to calculate the new centroid, we take all the data and we take the average of that data. So we take the average of feature x, we take the x1, we take the average of feature x2, and this becomes our new centroid. And we take all the data. We do not have hard clustering, so we don't just take all the values that are only in cluster 1, but we take all the values. However, weighted with this probability of the data point to actually belong to that cluster. So we do not have hard clustering, but we still have information. So data points that we previously kinda assigned to this cluster are playing bigger of a role in the new centroid than data points that we assumed to not belong to this that likely. And this is why this is called soft clustering. And this is it.